Lesson 98, Fundamental Theorem of Calculus, Part 2. Okay, now, let's review. What is Fundamental Theorem of Calculus, Part 1?
It is the integral of the one minus the integral of the other is the area, or is the distance between the two.
Okay. And I'm not always good about using the vocabulary, this is Fundamental Theorem of Calculus, Part 1 that we're doing. Okay, but we learned Fundamental Theorem of Calculus, Part 1 when we learned how to evaluate a definite interval. Okay, when we learned how to evaluate an integral that has boundaries. Okay, so we start off with the plus c, and then we learned, okay, when there's boundaries, we can plug them in and subtract. So, Fundamental Theorem of Calculus, Part 1, suppose f is a continuous function on the closed interval a to b. If capital F is any antiderivative of lower f, then the integral from a to b of fx dx is the antiderivative of b minus the antiderivative of a. Okay? That's Fundamental Theorem of Calculus, Part 1. Now, Fundamental Theorem of Calculus, Part 2. If f is a function that is continuous on some closed interval I, same old, and c is any number in that interval, then f has an antiderivative, capital F, on this number that can be described as follows. So, antiderivative of f is the integral, notice from c to x of f of t dt. With Fundamental Theorem of Calculus, Part 2, c represents a number, and then your top boundary will be x, or in other words, a variable. And what happens then, since f is an antiderivative of lowercase f, the derivative of f equals f. So the idea that, okay, if you look at that statement right there, okay, capital F of x is equal to the integral of lowercase f, because that is the antiderivative. So if you do the derivative of an antiderivative, well, that just takes you back to the regular f, right? So if we do the derivative of this integral, well, the derivative and the integral basically cancel each other out, and it's just equal to the function. And what ends up happening is it's equal to the function evaluated at that variable up top there. Okay? Now, example 1 has us practicing this. We're going to do example 1 2 different times. We're going to do example 1 using Fundamental Theorem of Calculus, Part 2, which is a shortcut. But we're also going to do example 1 using Fundamental Theorem of Calculus, Part 1, just so I can show you how they connect. And then after that, we're just using the Fundamental Theorem of Calculus, Part 2. So, as we look at example 1 there, simplify the derivative of the integral from 9 to x of t squared dt. Well, Fundamental Theorem of Calculus, once you understand it, you can just look at it and know the answer. The derivative and the integral essentially cancel each other out, right? They undo each other. And so then the function is t squared. So evaluated at x, so t squared evaluated at x is x squared. Okay, so that is x squared, and officially that is by the Fundamental Theorem of Calculus, Part 2. So FTC 2. Now, let me prove to you it is really just x squared. Okay? So, the derivative of the integral of 9 to x of t squared dt. We're going to do this the long way now. So, let's focus on the integral here. What is the integral of t squared? Okay, so the integral is, and if I'm just worrying about that piece, it's 1/3 t to the third, whoops, t to the third, that looks ugly, there we go, evaluated from 9 to x, correct? And if you put those in and evaluate, 1/3 t cubed evaluated at x is going to be 1/3 x cubed minus 1/3 t cubed evaluated at 9. So what's 1/3 times 9 to the third?
A big
It actually divides by 3. So 9 to the third,
273.
So
close.
81 times 9.
243? I was going to
I
say,
missed a number.
yeah. Now, okay, this piece right here that we just did was this integral from x to 9 of t squared dt, yes? But now, what haven't we done yet? We haven't taken the derivative of 1/3 x cubed minus 243. In other words, we just worried about the integral part. We never actually took the derivative part. What is the derivative of 1/3 x cubed minus 243? Yeah, derivative of 1/3 x cubed is x squared. Derivative of 243 is 0. Now, that was technically using fundamental theorem of calculus part 1. Pick your poison. Use fundamental theorem of calculus part 1 and do all that work every time. Or look at it and realize, okay, fundamental theorem of calculus part 2 allows us to make the jump. Are you convinced at least?
Yeah.
I felt like if I just said x squared and moved on to the next one, you'd be like, okay, kind of, whatever, if you say so. I'm hoping now you're a little more of a believer. Okay? Okay, so example 2. The derivative of the integral from x to 4 of sine t over t, given that x is greater than 0.
Well, numbers are in the wrong order.
Okay.
I saw earlier.
Numbers are in the wrong places. What will allow me to make that x magically be up top?
With the negative.
Flip the integral and do a negative. So let's rewrite this. It's d dx of the negative of the integral. Because I put negative out front, I can now say 4 to x of sine t over t dt. Does that make a little more sense to you? We had to give you the tricks right off the bat. So, the derivative of the integral, we've got that x in top where we want it. Well, you can do the long way. I'm just gonna expect the answer though. What are your thoughts?
Two schools of thought. It's either sine x over x, or it's negative sine x over x, because the negative this.
Thoughts on which one of Ross's answers we should go with?
I kind of feel like the negative.
Surely the negative one.
The negative, yeah. Because it's the negative times this integral. Okay? Or the negative times the derivative of the integral. So it is the negative of sine x over x. Okay, example 3. Simplify. d dx of 17 to the x of e to the negative t squared dt.
Would this just so happen to be as easy as e to the negative x to the 7?
Yes? No? Yeah. Sorry, you're expecting a trick after the last one, aren't you?
Yeah.
Yes.
I was waiting on that.
Just e to negative x to the second.
See if this was calculus.
Show this to Jace later and be like, this is what it's been like now.
This is what you missed out on all year long. Okay, questions there? Now, I know some of you caught me at the beginning of class. I was fixing a typo. So I know some of you are watching me, some of you were not. So what this is supposed to read is differentiate the natural log of x equals the integral from 1 to x of 1 over t dt with respect to x. Now, so they want us to differentiate the natural log of x. So they want us to take the derivative of natural log of x with respect to x. But they tell us the natural log of x is equal to the integral from 1 over x of 1 over t dt. So really what we're doing is we are differentiating the integral from 1 to x of 1 over t dt.
So that's what that was.
Now technically, you can do either of those pieces and get the same answer, yes? The derivative of the natural log of x, well that's one we know. Or the derivative of the integral from 1 over to x of 1 over t dt is going to be 1 over x. And again, that is by what we've been using all day, Mendel-Mann's theorem of calculus, part 2.
Well,
Okay.
what's the catch?
I'm going to write down your changes in homework. Ethan's going to like a couple of these.
I'm skipping them.
I feel like we're
Well, first of all, number 2 becomes number 9 from 77. And then I have written down that we're going to skip 10 and 18. And we're going to skip not 15, but 15 CD. Sorry, I didn't want you to be like, oh, and we're skipping 15. Skipping 15 CD.
Going all the way back to 77.
Which means that's where the problem came from, is 77, which is one of the lessons we skipped.
Guys, I'm not sure if I'm going to be able to do it myself after we don't have 25 questions.
I'm not gonna wake up